Hi, my name is Daniel Kang, and today I'll be talking about accelerating approximate aggregation queries with expensive predicates. This is joint work with my colleagues at Stanford University and the University of Chicago. Domain experts want to increasingly query unstructured data. For example, a query might take the form, compute the average sentiment of articles on the New Deal and historical newspaper scans, or compute the average number of cars at red lights. And a common query is an aggregation query with a predicate. For example, turning this query into a SQL form would be of the form select average sentiment of article from newspapers where the article talks about the New Deal with some budget. And this would return something of the form 73% positive. Unfortunately, however, predicates are expensive over unstructured data sets. For example, DNNs can run as slow as 3 frames per second on accelerators or images per second. And if we execute this on the public cloud, this will cost over $1 million in cloud compute credits for 100 camera months of video, which is prohibitively expensive for many applications. Recent work has proposed using proxies to accelerate queries. And can we use this to help? Well, the way this is most standardly done is we execute a proxy over all the data because it's substantially cheaper than these expensive deep neural networks. Generate a proxy score, and then return records, and then only sample the oracle on records where the proxy is unsure. And so these proxies can reduce query costs for selection and whole dataset aggregation queries. A key requirement, though, is we want statistical guarantees and accuracy in the form of a confidence interval because we can't execute the expensive predicate over all the data set. And so the answer would actually be of the form 73% positive plus minus 5%. And unfortunately, because we require these confidence intervals for scientific analyses, prior work on selection and aggregation does not directly apply to accelerating these queries. In particular, for work on selection, the statistic of interest, for example, the sentiment, might be correlated with the predicate. And because there's no guarantee on what records are returned, this might bias the results in an unknown way. And for prior work on aggregation, for example, Blazeit and BLDB 2020, requires that the proxy value on all the records of interest. But unfortunately, we don't know what records are of interest before executing the expensive predicate on the records. And so in this talk, I'll describe how to accelerate aggregation queries with expensive predicates with guarantees on accuracy. I'll first describe our algorithm ABae, and I'll then describe our theoretical analysis for ABae, and I'll conclude with the evaluation. I'll first start with a problem statement and some notation. Define Y to be the statistic. In the prior example, this would be the sentiment, and P to be the predicate. Here, this would be articles on the New Deal. The goal is to estimate the following quantity: the expectation of Y conditioned on P equal to 1. And we want to do this with as low error and confidence interval width as possible. So how do we do this naively? Well, we can turn to sampling. And to do this, we could do uniform sampling and then discard irrelevant samples. Here, the samples that satisfy the predicate are in blue and the ones that don't are in red. And then we can compute the mean and return the answer. Unfortunately, this is inefficient for rare events because most of this budget is basically wasted on these red records, which aren't relevant to the query at hand. And so instead we propose ABae, which leverages proxies for more efficient sampling. What I'm showing here is a data set where the higher proxy scores are on the left, where the records with higher proxy scores are on the left, and the records with lower proxy scores are on the right. Instead of standard random sampling, we first stratify by proxy score, generating these strata. Then we estimate the optimal allocation and then using pilot sampling and sample according to this estimate. And so as we can see, we sample more from the left because there are more blue records there. So to do this algorithmically, we do the following. We first sample uniformly to obtain estimates for the predicate positive rate, which we call P sub k, and the variance sigma sub k squared. And this is per strata. Given these estimates, we estimate the optimal allocation as T star sub k, this is per strata, to be proportional to root P sub k, the predicate positive rate, times sigma sub k, which is a standard deviation. And then we draw samples according to this estimated optimal allocation. To generate confidence intervals, we use the bootstrap, and we generate samples via ABae, and then we bootstrap resample each strata to generate the new estimate. And then we return confidence intervals from the bootstrap samples. Compared to standard query processing, this is where the bootstrap is quite expensive. It's actually quite cheap in our setting because the predicates themselves are so expensive that we can run this procedure with many resamples to get tight confidence intervals. Now that I've described ABae's algorithm, I'll describe our theoretical analysis, which requires new tools for analyzing our setting. In particular, because we have a stochastic draw of drawing a sample of interest. The first thing we show is that ABae matches rates of the optimal allocation. And so the optimal allocation that minimizes the mean squared error is proportional to root P sub k sigma sub k. And the optimal MSE is this expression, which is on order, in which the error decreases on order 1 on n. And what we show in the full paper is that ABae achieves an MSE of O of 1 on n. And I don't have time to go into the full technical details in this talk, but please see our full paper and the extended proof document for how we prove this and the new techniques that we use to study the setting. We also show that ABae's bootstrap is asymptotically valid. To do this, we define y sub k to be the statistic and p sub k to be the predicate per strata. And then the bootstrap validity follows from the Hadamard differentiability of the n statistic, which is defined here. And this looks quite complicated, but it's essentially a rewritten expression for our sampling procedure. And please see our full paper and proof document for the full details. So now I've described ABae and its analysis, and I'll just talk about our evaluation. In the full paper, we evaluate on 6 real-world datasets, including videos, images, and text datasets. The cost metric is target DNN identifications. This is the budget, which is held fixed. And the accuracy metric is the root mean squared error to be on the same units as the confidence interval width, which is our other accuracy metric. The first thing we show is that ABae outperforms random sampling on the metric of root mean squared error. As we can see, ABae is on the bottom here, where lower is better, and we can achieve 2 times fewer samples for fixed mean squared error, and a 1.6 times lower MSE for a fixed budget. We also show that ABae outperforms random sampling on the metric of confidence interval width, and similarly here on the y-axis I'm showing the width, and on the x-axis I'm showing the budget, with ABae on the bottom. We can achieve 2 times fewer samples for fixed confidence interval width, and a 2 times tighter confidence interval width for fixed budget. And this is a substantial improvement, especially when human labelers need to verify the deep neural network for scientific analyses. And so in conclusion, aggregation queries with predicates are common, but unfortunately existing techniques do not work well. And we can achieve statistical guarantees in accuracy while improving performance by up to 2 times with ABae. And the analysis requires new techniques. My email is here, and I'll also be around to answer any questions that you might have. And thank you very much for your time.